Today's lesson is going to cover triangle vocabulary, the triangle inequality theorem, and the side angle theorem. For the triangle vocabulary, so again, recall that all vocabulary will be circled. And I will go ahead and tell you the definition. So now is a great time where we can really use YouTube, that the student can pause it and record that definition however quickly or however slowly you need to, and then push play again and we can move on to the next one. So this first triangle up here, what do you notice about those sides? Well, you'll see that this one only has one tick mark, this one has two, and this one has three. Those sort of tick marks along the side length are used to describe the sides, the lengths of those sides. And what we can see here is that none of them are the same. So this is a scalene triangle, a triangle where none of the sides are equal, or all three sides have different lengths. In the middle here we have an isosceles triangle. And you can see that there's one tick mark, here's two, and this one's two as well, which shows you that this side and this side are the same length. An isosceles triangle, as you may guess, is one where two of these side lengths are equal. Our third triangle here is an equilateral triangle. What do you notice about equal? All three sides are equal. They each have one tick mark, which means that they all have the same length. These three words are used to describe triangles by their sides. So these don't tell us anything about their angles. For their angles, we have other ways to describe them. We can describe them as obtuse. And you can see that this angle right there is an obtuse angle. So an obtuse triangle is one where one of the angles is obtuse and two are acute. Again, an obtuse angle is one that has a measure larger than 90 degrees, but less than 180 degrees. This second triangle here is an acute triangle. All three of the angles are acute. An acute angle is an angle that measures less than 90 degrees. This is a right triangle. A right triangle has one right angle, which measures exactly 90 degrees. The other two angles here are acute. And this is a funky word to say that equiangular. Again, we see this equi. And before we thought it meant equal, it does again. This means that all of the angles are equal. And I've drawn two lines in each of them, same as up here with the tick marks, to show that they are the same. First checkpoint. Describe each of these triangles by their sides and angles. So now would be a great time to pause, record your answers. You can label this one 1 and this one 2, and we'll go over them in class. Next up, we have the triangle inequality theorem, which states that any side of a triangle is always shorter than the sum of the other two sides. So I just drew any sort of triangle here. I could have drawn a right triangle, an acute, an obtuse, doesn't matter. This is always true. And it says that any side is always shorter than the sum of the other two. So if I add up A and B, that has to be greater than C. So C has to be less than A and B. Same with B plus C. Has to be greater than the third side, A. A and C, their sum has to be greater than B. Why is this? Well, you're going to learn that in class today using Twizzlers. One example. I drew another triangle here. And here I drew it with, well, let's read the problem. If C is equal to 4 and B is equal to 11, I didn't give you units, I should have. What are the possible values of A in triangle ABC? So we know that C is 4 units and B is 11 units. We're trying to figure out what A is, the red one. And here I've tried to draw it where A is as small as possible, because you can see that B and C, there's a very small angle between them. They're almost on top of each other. So A is going to be as small as possible. Versus here, B's here, C's here, going back, and C, they almost make a straight line going not towards each other, but away from each other. So A is as large as possible. We see that following the same formula up here, A plus B is greater than C. I just copied this and color-coded it with the sides. And now let's look. Let's fill in the values that we know. we can fill in 4 for C and 11 for B because we were given 2 of the side lengths. A plus 11 is greater than 4. 11B plus 4C is greater than A. We're trying to figure out what A is. And for this last one, we get A plus 4 is greater than 11. Now we need to solve these inequalities. When we solve inequalities, unless you're dividing or multiplying, just think about them as an equal sign. So if we have A plus 11 is greater than 4, we want to get A by itself. We want to figure out not what A plus 11 is greater than, but just what A is greater than. So if we have a plus 11, we need to do the inverse function. The inverse of the opposite of addition is subtraction. So we subtract 11 from both sides, and we're going to get A is greater than negative 7. You're always going to get one of these with the side length greater than a negative number, and of course it's greater than a negative number because side lengths are positive, so you can just ignore that one. But you're always going to get one that's negative. For this next one, 11 plus 4 is greater than A. We don't need to move anything across the greater than sign, so we can just combine like terms, the 11 and the 4, to say that 15 is greater than A. Lastly, we have A plus 4 is greater than 11. We need to get the 4 over to the other side, so we subtract 4 from both sides. A is greater than 7. So we have 15 is greater than A, and A is greater than 7. So A is between 7 and 15. So 15 is greater than A, which is greater than 7, or we usually write it with a smaller number first to say that 7 is less than A, which is less than 15. So now we can check our answer. We can pick a number between 7 and 14 and put it in here and make sure that any side is always shorter than the sum of the other two. So let's pick 8. If I pick 8, which is, pretty close to 7, so maybe it won't work. Let's pick 8. And let's say 8 plus 4, that's 12. That's bigger than B. 8 plus 11. Yep, that's definitely bigger than 4. 11's already bigger than 4. And now let's try C plus B. 4 plus 11 is 15. That's bigger than 8 too. All right, we're good. We could check that with all of the numbers between 7 and 15 just to double check. Next, we have the side angle theorem. This is a great way to help us really understand triangles and how they work. The side angle theorem states that the shortest side is always opposite the smallest angle, and the longest side is always opposite the largest angle. So I've drawn a picture here, and I've highlighted in colors the longest line segment of the triangle and the biggest angle. And you can see that they are, in fact, across from each other. They're opposite. The shortest is in green, 30 degrees, and the side length opposite that is 12.9 centimeters. 50 degrees, the side opposite that is 19.7. And as we can see here, as the degrees get bigger, the angle gets bigger, so do the side lengths. So let's think about this. What does this tell us about isosceles and equilateral triangles? Remember, isosceles is a triangle where two sides are the same, and an equilateral triangle is a side where all three sides are the same. So let's take a look at this triangle. First, I know that this means it's a right angle. Okay, cool. So I have a right triangle and it's isosceles because two of my sides are 5 centimeters. So I have an isosceles right triangle. I know that the angle measure across from one of these sides is 45 degrees. Now, I know that the shortest side is opposite the smallest angle, and the longest side is opposite the largest angle. But what if the sides are the same? So if the sides are the same, or even if the angles are the same, so if the sides are the same, the angles also have to be the same that they're across from. If the angles are the same, you can make the same conclusion about those sides. If I know that this is 45 degrees, and that's 5 centimeters, and I know that that's also 5 centimeters, what do you think that the measure of these degrees is going to be? it's also going to be 45. Let's say I wasn't given these side lengths, just that these two angles were both 45 degrees, I could come to the same conclusion. In this example, I have an equilateral triangle. I told you that one of these sides is 3.14 inches. Now we know in an equilateral triangle that all of these sides are the same. So if this is 3.14 inches, 3.14, that number seems familiar, then I know that this one is as well, and this one is as well. So if this is 3.14 inches, and it's across from a 60-degree angle, what do you think I can conclude about these other two angles? They have to be the same. And they have to be the same because there's no shortest side and there's no longest side. So the angle measures can't be different. Because if this were 30 degrees, then I would know that this were the bigger side. Let's take a look back at this triangle. These two are 45 degrees. We made that conclusion. This one's 90 degrees. Do you think that this side length is going to be bigger than or less than 5 centimeters? I'll let you guys write that down and bring it to me in class.